application regarding time independent Schrödinger equation. Example number 2. In this we'll apply this time independent Schrödinger equation regarding finite square potential well. A particle will be within a finite square potential well, and we'll find a wave function and for different regions, and then find the energy levels corresponding to this particular problem. And this is the this finite potential well. Here we see that there is a finite length of the well. This is something called minus v naught, and this figure clearly depicts that the well is of finite depth and having a depth of minus v naught. So we have three regions here where the potential is 0 for x less than minus L and x greater than L. This is region 3, this is region 1, and this particular region inclusive of these two sides is the region number 2, which is defined as minus L equal or less than x, and x less than or equal to capital L. So x greater than minus L or equal to minus L, and x less than or equal to capital L. So in this region the x is between minus L to L, and here the potential is minus v naught, with v naught being a constant. And this potential one interestingly allows us two states. One is bound state and another one is scattering state, whereas we define a bound state by negative energy and a scattering state by positive energy. So we'll discuss first the bound states and then proceed to find out for scattering state, that is E greater than 0. So let's firstly discuss about E less than 0 bound states. So definitely that in the region x less than minus L, that is region number 1, the time independent Schrödinger equation is this, where this alpha square is this, and since alpha is a real quantity and E is negative, so definitely this quantity is plus, and this quantity is plus means this alpha is a real thing. Now the general solution of this equation 1 is this, and since x tends to minus infinity, the first solution will become diverging, because minus infinity will make it plus infinity, and so it will diverge out, and so it will be physically unacceptable solution. So we'll be left only with this solution b e to the power alpha x, and this 1 representing region number 1, that is x less than minus L. So equation 3 represents the solution for region number 1. In the region 2, the Schrödinger equation is this plus beta square, where we put this beta square equal to twice mb plus v naught, and here although E is negative, but it must be greater than minus v naught, because E must always be greater than v minimum, so that beta is always real and positive. So although this E is negative, it must be greater than this minus v naught. The magnitude must be greater than minus v naught, and that's why this particular beta square is a positive quantity, and that's why beta is real. And then general solution of equation 4 is this one, where this 2 represents the solution corresponding to region 2, and it is c sine beta x d cos beta x. These are all from our common knowledge of differential equation, where there's plus beta square representing exponential solutions, and since imaginary part is there, so they lead to some cosine and sine function. So equation 6 is the solution of equation 4. And here also these constants c and d are arbitrary, and we have to find them out. And the region T, the solution is same as that of region 1, but with some different coefficients, f e to the minus alpha x plus e to the minus alpha s. But here, since the region is x greater than L, so if x tends to plus infinity, that would make that this g e to the power plus infinity will make it as diverging term, and that's why this term will have to be neglected. since the region is x greater than L, so x is positive. So if x tends to plus infinity, then definitely this is diverging and we have to drop this term. So for the region 3 we are having this term given by equation 7, f e to the minus alpha x. Now the boundary and continuity conditions are this, that at the boundary of first and second region these wave functions are continuous. So wave function in region 1 is equal to wave function in region 2. Similarly, wave function in differentiation of that means they are also continuous first derivative. So differentiation of ui at region 1 is equal to differentiation of second wave function at region 2, that is at x equal to minus L. And similarly here at x equal to L, that is this x equal to L representing the boundary between region 2 and 3. Here also the wave function in region 2 must be equal to wave function in region 3. And similarly their derivatives also have the equal values. So these are the boundary conditions which we have already discussed earlier on. So using these boundary conditions and also the fact that since the potential is an event function, so we will consider solutions either odd or even. That means it's if x is minus, then it may be plus ux or minus ux depending on odd or even. So this is advantageous because imposing the boundary and conditions on one side, say x equal to L, would make it automatic for the other side also. So we'll at the boundary conditions given by these equations will be manipulated by one further condition, that potential is an event function. Because of even nature of the potential function, will impose these conditions, and in that sense now the solutions using all these boundary conditions would lead to this kind of things. Ux equal to f e to the minus alpha x, it is for region t, d cos beta x for this region, and this is for x less than 0. That means the x equal to minus L. So this equation 8 are all the solutions, and we are taking only the event solutions. Now the boundary conditions at the point x equal to L would give us this one from equation 8, and from equation 8 we have these two conditions, f e to the power this minus alpha L equal to d cos beta L, and minus alpha L f e to the power minus alpha L minus beta. So this boundary condition, the first boundary condition is giving us this 9 and 10, first condition equation 9, second condition equation 10, and dividing 10 by 9 we get alpha equal to beta 10 beta L. So this is very simple, just we simply divide this quantity by this, and this minus minus goes, and ultimately we have beta 10 beta L for alpha. And this equation relates to alpha and beta, and since we know that alpha and beta are simply energies, so this equation will be very useful in the later course of time. And also we put y equal to beta L and then y not equal to this one with this imposition of 12 in the 11, and also 2 and equation 2 and 3, 2 and 5 here, we get alpha square per beta square equal to this, and ultimately with some simplifications this alpha L equal to y naught square root of y naught square minus y square. So equation 11 ultimately can be put in the more convenient form, 10y equal to square root of y naught by y whole square minus 1. That is equation number 13. So this is a transcendental equation where y is a function of y naught, and numerical solution is always necessary for this kind of transcendental equation, or some kind of graphical plotting is always necessary. So by plotting this 10y versus this particular quantity, we can find a point of intersections, and from that we can define different kind of quantities which should give us energies in terms of alpha and beta. So we will consider two limiting cases. For case 1 we will consider this wide and dipole. This means that the width of the well is quite large, and in that case y naught is very large, and intersections occurs slightly below this value, and with n being odd, and This means that equation 5 and 12 will lead to this condition, En plus B not equal to this, where n is simply some odd numbers. The right hand side of 14 is simply a infinite square energies. If you remember, infinite square potential energies here, and with the width of twice L here, because we are considering the width of the well as from minus L to plus L, or half of them is as n is odd, whereas E plus B represents B naught represents the energy above the bottom of the well. Or we can say that this expression represents half of the energies that we can count out in case of infinite square potential well. Also, if V naught tends to infinity, definitely this finite potential well will be turning into infinite potential well, and the energy expression will become the same. Of course, for finite V naught, there are also some finite number of energy states. So for wide and deep potential Y naught is very large, we have energy expressions given by equation 14 with n equal to 135. And then for a shallow and narrow well, this is case number 2, where Y naught is very small. In that case, we have only very small number of bound states. And finally, for only until this condition is satisfied, Y naught less than pi by 2, we have only one such state. So this means that if the well is very weak, that there remains only one bound state. So for a second case, this shallow and narrow well will have only one bound state under these conditions, Y naught less than pi by 2. Whereas in the wide and deep well, there are large number of bound states were found, where Y naught is given by this, with n being odd 135. So this is what about the different energy states and wave functions regarding the bound state. Let's now discuss about Schrödinger states where the energy is positive. And similarly, for the reason this x less than minus L, the solutions are like this. Here we replace this alpha by alpha prime now, and again this alpha prime in real and positive, and since E is greater than 0, so definitely this alpha square is positive, and so alpha is real now from 16. This is similarly for equation 2, the solutions are same in a way. This is sin beta x d beta x, where beta is similarly defined as in equation 5. And for reason 3, we have these solutions, since there is no incoming wave, so the solution is e to the power f e to the power I alpha dash x. So so incoming wave is not present in region 3 for Schrödinger state. So this the e to the power minus I alpha x part is absent here. So the next thing is that we need to find out this A, B, F, and definitely they are related with incident amplitude, reflected amplitude, and transmitted amplitude. Now again we are using the boundary and continuity conditions. First, at x equal to L, at x equal to L, U1 is equal to U2, and D differentiation of U1 is equal to differentiation of U2. So using those conditions at the region x equal to minus L, our solutions 15 and 17 lead us to these equations 19 and 20 respectively. And then similarly at the region x equal to L, this is the boundary between the region 2 and 3, whereas using these boundary conditions U2 equal to U3, that is wave function, and region 2 is equal to wave function in region 3, and first derivative of wave function in region 2 is equaling first derivative of wave function in region 3. They also, this continuity and boundary condition will lead to these equations 21 and 22 respectively, where we are using the wave functions given by 17 and 18, because we are considering region boundary between the regions 2 and 3. So with this all and then simplifying, just like 21, multiplying 21 by sin beta L, then 22 by cos beta L, and then doing all these simplifications, we get the C expression for C like this, given by equation 23. And similarly, multiplying 21 by cos beta L, and then equation 22 by sin beta L, and subtracting the second from the first one, we get D equal to this one, cos beta L I alpha dash by beta sin beta L whole square square bracket and f e to the power I alpha dash L 24. So C and D are thus determined. Now substituting 23 and 24 back in equations 19 and 20. If you see here 19 and 20, we get the expression for B here in terms of f with these coefficients given by equation 25. So it's just some simplifications. We use 23 and 24 in equation 19 and 20, where we in 19 and 20 we see that A and B are connected here, and we are trying to drop off this B terms, or sorry, A terms in terms of this C and D as obtained from 23 and 24. So we have an expression for B here, and then the same way we get an expression for f in terms of A here given by equation 26. Since the transmission coefficient is modulus square of f square by A square, so using 26, 16 and 5 we get a relation like this, that inverse of this transmission coefficient is equal to 1 plus v naught square divided by 4e bracket of e plus v naught sine square and this quantity given by equation 27. So all are some simplifications. We are using 26, 25, 26 for this transmission coefficient, and simply this from this definition for transmission coefficients, and also using 16 here, and also the expression for beta square from 5, we get an expression like 27. One thing is that if this sine term is 0, then t is equal to 1. That means that the full transmission is possible there, and in that case that t is equal to 1, that means we have the energy levels like this. So through some simplifications with n equal to 0, 1, 2, 3, all integers. Now also one thing that that t equal to 1 is possible only when, if you look at equation 28, only when this condition is satisfied, and this is nothing actually, this is the energy levels which we discussed in case of infinite square potential well. So this is what about Schrödinger states, the energy levels given by equation 29, and we are having some wave functions here for n equal to 1, n equal to 2, n equal to 3, and on the other side here we have these probability densities, this one, and then this is the graphical representation for the transcendental equation 11, where the intersecting points are very important regarding the determination of value of y naught and the condition for allowed energy states. And also this is the variation of transmission coefficient with respect to energy for a Schrödinger state, which is just discussed here in using the equation 28 or 29. So with all this we can conclude that we, in case of the finite square potential, we have two cases. One is bound state, E less than 0, and another case where E greater than 0, that is Schrödinger state. And for both the states we have energy levels and using the boundary and continuity conditions on the wave functions, and very carefully we find out the wave functions for region 1, 2, 3, where it has specified in the diagram, where region 1 leads to region 1 represents x less than minus L, and region 3 representing x greater than L, and that means that the first region is in the negative x region, and then region 3 is in the positive x region, and also the region 2 is in between the two, where we show a deep well in the first slide. So in the first slide here, this is the region 2, region 1, and using all these continuity and boundary conditions, we find out all these coefficients A, B, C in both the cases, and ultimately leading to the energy levels. So this is how we do, and we are due to time constant, I am avoiding some kind of mathematical calculations in a detailed way, but however that simplifications can be made with with a very simple way in order to get questions like 23, 24. They are not hard. Also, one thing that we must remember here is that we're considering a potential or event potential, so that the equation 8 are the wave functions regarding the bound state. We have to remember this thing while doing all this applying those boundary conditions for the bound states. So lastly, we are left with some kind of assessment. The potential representation, the graph which we show in the first slide, then the equation representing the bound state case, and for both the cases where wide and narrow well of the we have discussed. In the third case, scattering case, and also the graphical representation for the wave functions, probability density, and the transcendental equations. So with this I'm ending up this video. Hope the video is enjoyable for you. Please keep watching, and also put some suggestions whether to improve the videos. With all this, thank you once again. Bye.